Hello, good morning. Myself, MB Gaddi, lecturer in AC department. Today I am going to discuss regarding introduction to waveform coding. In continuous wave modulation, some parameter of a sinusoidal carrier is varied continuously in accordance with the message signal. This is in direct contrast to pulse modulation, which we study in this unit. In pulse modulation, some parameter of a pulse train is varied in accordance with the message signal. On basis, we may distinguish two families of pulse modulation. One is analog pulse modulation, in which a periodic pulse is used as the carrier wave and some characteristic feature of each pulse, amplitude, duration, or position, is varied in a continuous manner in accordance with the corresponding sample value of the message signal. In analog pulse modulation, information transmitted basically in analog form, but the transmission takes place at discrete times. Introduction to waveform coding. Digital pulse modulation, in which message signal is represented in a form that is discrete in both time and amplitude. Figure shows coded pulses which represents 0 and 11010, etc. That is, plus V indicates 1 volt, minus V indicates 0 volt. Pulse code modulation. The figure shows the graph versus encoded output and with respect to time. Pulse code modulation. Differential pulse code modulation. Differential pulse code modulation (DPCM) can solve the problem by transmitting the amplitude difference of the two successive samples instead of the actual samples. Figure shows differential pulse code modulation working and application. The graph is plotted against the decimal numbers 1 to 7, that is converted into binary, then sampling times TS, 2 TS, etc. up to 10 TS. DPCM, which exploits the use of lossy data compression to remove redundancy inherent in a message signal, such as voice or video, so as to reduce the bit rate of the transmitted data without serious degradation in overall system response. In effect, increased system complexity is trade-off for a reduced bit rate, therefore reducing the bandwidth requirement of the PCM. One more, delta modulation. Delta modulation DM, which addresses another practical limitation of PCM, the need for simplicity of implementation when it is a necessary requirement. DM satisfies the requirement by intentionally oversampling the message signal. Increased transmission bandwidth is traded off for reduced system complexity compared to PCM. DM may therefore viewed as the dual DPCM. PCM pulse code modulation is robust but demanding in both transmission bandwidth and computational requirements. DPCM, which provides a method for the reduction in transmission bandwidth but at the expense of increased computational complexity. DM, which is relatively simple to implement but requires a significant increase in transmission bandwidth. DPCM, the use of PCM for the digitization of voice or video. The signal is sampled at slightly higher than Nyquist rate. The resulting sampled signal is then found to exhibit a high correlation between adjacent samples. The meaning of this high correlation is that the signal does not change rapidly from one sample to the next, with the result that the difference between the samples has a variance that is smaller than the variance of the signal itself. When these high correlated samples are encoded, as in PCM, the resulting encoded signal contains redundant information. By removing this redundancy before encoding, we obtain more efficient coded signal. Figure shows DPCM transmitter and receiver. Figure A shows transmitter, sampled input x n of ts, then summary is there, e n ts quantizer, then output is given to predictor, then ENTS is the difference of the sampled input and the predicted output, often called as a prediction error. Similarly, DPCM receiver is shown. Delta modulation, which is 1 bit or 2 level version of DPCM, is precisely such a scheme. In its basic form, DM provided a staircase approximation to the oversampled versions of delta modulation. Above figure shows delta modulation. The binary sequence, then staircase approximation is shown in figure. Delta modulation, the difference between input and approximation is quantized into only two levels, namely plus or minus, corresponding to positive and negative differences respectively. Figure shows delta modulation system, transmitter and receiver. Then in delta modulation, a granular noise is occurring. It occurs when the step size delta is too large relative to the local slope characteristics of the input waveform x of t, thereby causing the staircase approximation u of t to haunt around relatively flat segment of the input waveform. So there is a need to have large step size to accommodate a wide dynamic range, whereas a small step size is required for the accurate representation of relatively low signals. The optimum size that minimizes the mean square value of the quantizing error in a linear delta modulator will be the result of a compromise between slope overload distortion and granular noise. Slope overload. Above figure shows slope overload. When the analog input signal changes at a faster rate than the DAC it can maintain, the slope of the analog signal is greater than the delta modulator can maintain and is called slope overload. Granular noise. It can be seen that when the original analog input signal has a relatively constant amplitude, the reconstructed signal has variations that were not present in the original signal. This is called granular noise. Granular noise in delta modulation is analogous to quantization noise in conventional PCM. Comparison between PCM and DM systems. Here, parameter, first table parameter, second PCM, DPCM, delta modulation, and adaptive delta modulation. This table shows comparison between pulse code modulation, differential pulse code modulation, delta modulation, adaptive delta modulation. First point, number of bits per size in PCM 4, 8, 16 bits. In DPCM more than 1 bit but less than PCM. In delta modulation 1 bit. In adaptive delta modulation 1 bit. Similarly, number of levels in PCM depends upon the number of bits. In a DPCM, fixed number of levels. Delta modulation 2 levels. Adaptive delta modulation 2 levels. Step size in PCM fixed or variable. In DPCM fixed or variable. Delta modulation fixed one. Adaptive delta modulation variable. Transmission bandwidth, more bandwidth is needed in PCM, less than PCM, delta modulation lowest, ADM lowest. Then similar way, quantization noise or distortion. In PCM, quantization noise depends on number of bits. In a DPCM, quantization noise and slope overload. In DM, slope overload and granular noise. ADM, quantization noise only. Complexity of implementation. PCM, it is a complex one. DPCM, it is a simple one. DM, it is a simple one. ADM, it is a simple one. Need for adaptive delta modulation. To overcome the quantization errors due to slope overload and granular noise, step size delta is made adaptive to variations in the input signal x of t. In the steep segment of the signal, the step size is increased. On the other hand, if the input is varying slowly, the step size is reduced. This method is known as adaptive delta modulation. The adaptive delta modulators can take continuous changes in the step size or discrete changes in step size. Figure shows adaptive delta modulation transmitter. It consisting of elements, 1 bit quantizer, logic for step size control, delay, then summer, output, the adaptive ADM transmitter. ADM transmitter. The logic for step size control is added in the diagram. The step size increases or decreases according to a specified rule depending on the 1 bit quantizer output. If 1 bit quantizer output is low, the step size may be reduced by 1 step. Figure in next slide which will be shows staircase waveforms of ADM and the sequence of bits to be transmitted. It is called adaptive delta modulation. ADM receiver. In the receiver of adaptive delta modulator, there are two options. The first portion reduces the step size from each incoming bit. Second point, the previous input and present input decides the step size. It is then applied to an accumulator which builds up staircase waveform. The low pass filter then smoothens out the staircase waveform to reconstruct the original signal. Figure shows ADM receiver. It consisting of input, logic for step size controller, then a delay, then low pass filter, then output. Advantages of ADM. The signal to noise ratio becomes better than ordinary delta modulation because of the reduction in slope overload distortion and idle noise. Because of the variable step size, the dynamic range of the ADM is wider than the simple DM. Utilization of bandwidth is better than the delta modulation. Next, one more point is quantization. Many signals such as speech have a non-uniform distribution. The amplitude is more likely to be close to zero than to be at higher levels. Non-uniform quantizers have unequally spaced in unequally spaced levels. The spacing can be chosen to optimize signal to noise ratio for a particular type of signal. Figure shows the quantization. Varying step size reduced with reduction in noise, reduction in signal level. For weak signals, step size equal to small. NQ reduces, SNR improves. Hence, step size is varied in such a way that SNR equal to high. This is a non-uniform quantization. Non-uniform quantizers are difficult to implement as it is unknown to about advanced changes in the signal level. An alternative is to first pass the speech signal through a non-linearity before quantizing with a uniform quantizer. The non-linearity causes the signal amplitude to be compressed. Weak signals amplified, strong signals saturated at a level. At the receiver, the signal is expanded by an inverse to the non-linearity. The process of compressing and expanding is called companding. Companding equal to compression plus expansion. Companding model and its characteristics. M of t is the signal which is applied to a compressor, next which will be given to a uniform quantizer, then output will be expander. Figure shows compressor characteristics and expander characteristics. Companding characteristics figure shows